Okay, let's get back to this. So this is just a figure. Oh, what happened? This is a figure we showed before. So just a continuous system block diagram, how each component was named. I think recently, because, or not recent, after the development of the control computer and the particular microprocessor, microcontroller, it become very, very low cost. You can get like a few bucks to get a microcontroller. So mostly, if you get a design system nowadays, it's all going to be digital controller. I think could never imagine you're going to do an analog controller anymore. Analog controller normally is implemented through resistors, capacitors, and inductors. Then you get an operational amplifier. If you're from SECTI, you're familiar with this stuff. And these stuff can be used to do the calculation. Okay? So this is called operational amplifier. Very simple kind of method to change the signal. Capacitor and the inductor is to change the kind of phase of the system. So combining all these stuff, you can design a desired kind of controller using circuits. But this will become very chunky, take a lot of space, and the main problem is you can't really make any design changes once it's done. Because physically you have all these components like physically connect to each other. With digital controller, the benefit is obvious because your control theory is a piece of program. You can very easily just change the program without touching any hardwares. And that's also the kind of the feature and the advantage of PLC is because it's kind of mostly the calculation and the control is achieved through the PLC software. So most of the wire connections are fixed. You don't have to touch that. So make the change of your logic much easier. Okay, so here are a few kind of examples. So pretty much everything is a digital control nowadays. Only like very old machines, you never touch it in the last 30 years, still have some analog circuit control. For the control system, one and the most important thing when you design it is to make sure it is stable. Stability is always something when you design a controller you have to check and make sure that stability is absolutely stable. Okay, so these are 4 different figures for the system stability. Just quick question: is this stable? The first figure stable? Yes or no? Yeah. Anybody? Just can you just click the green button? Say yes or let me change my. Yes. First one is nobody say no. Anybody say no? How about the second one? The one on the right. The second one, is this one stable?
Yes.
Yes. Anybody say no? Second one, anybody think it's not stable? Because you see it's kind of oscillation a little bit. Okay, or think it's stable. Third one. Stable or not? No? Unstable. Well, fourth one, it's already set here. Sorry, it's the solution is already given. So the first 2 is are stable. The third and the fourth is unstable. What we normally get is this situation and this situation. The first and the third one is kind of extreme cases. So our control system normally have something a little bit oscillation, then it either goes stable, a little bit oscillation, or goes unstable. Huh? One of the key things when you design, you don't just check are the systems working fine. You have to make sure it's stable, and not just stable at its normal working condition. It needs to be stable with disturbance, with the noise, with other disruptions. Okay? So it needs to be absolutely stable. So even you have to check it's stable enough, even you have external disruption, it is not enough to trigger the system into an unstable condition. So you have to have a certain range of stability. This is a diagram of the system. So this is called a step response if you haven't learned control theory. So the input is basically this dot line, this 1, 0 dot line. So that's your input. And the design output will be exactly like that input. However, for a control system, the system itself normally has a dynamics. Anybody knows like why a system has dynamics? Or what kind of system has dynamics? Anybody can give me a short explanation? When we do all these control systems, we all get weird. Why the output is not just directly the same as input? Why the system has dynamics? What like physically, what it is? What is this dynamics thing? Anybody knows? Anybody give it a try? Just unmute yourself and pop some ideas. Why do we call a system has dynamics? Physically, what is dynamics? Anybody knows?
Is it because the system is constantly changing?
Well, this right.
Constantly changing. Well, that's some idea. Anybody wanna give another try? Another idea?
Doesn't have to do with movement, right? If it's static, it's not moving. If it's dynamic, it's moving.
Well, so you're definitely from mechanical engineering. I think this time when we saw dynamics is probably a different concept. So can we get an example of some systems don't have dynamics? Do we have any system don't have dynamics?
Or something would not be dynamic because it's just on off.
Even that is, if even you have a switch, it will have some dynamics. So dynamics means the system actually have certain way of storing the energy. If your system doesn't have any energy, it doesn't have dynamics. So your input is pretty much, you can consider it's energy, goes to the system. The output is how the system responds to the energy. However, almost everything, when you have some input, it will take some time for the system to respond. So if you have the system is, you have to make the move, any system has mass, or everything have mass, right? It will have some inertia, and it takes time to change its moving condition from Newton's law, right? So that system has dynamics. So any system with mass will have dynamics. And then also, if you have a spring, it also have dynamics because it can store energy. So a dynamic system is normally we refer to a system can store energy. The system will have some way of storing energy and then release energy. If it's electrical motor, it turns an electrical signal into a mechanical movement. So the process will take some time from the input to the output. It doesn't go just straightforward. It's not like an equation. You can put an equation there, the input is twice of output. It just, whatever you got to input, it multiply by 2. But the physical system doesn't work like that. So that's why we call a system has a dynamics, or call it dynamic system. So almost all the kind of mechanical, electrical system will definitely have dynamics because it's have energy going through. The for mechanical system, you have electrical energy, you have inertial energy turns into movement, and then sometimes movement turns into inertia, and become inertial energy. So it's kind of energy turning between different type. So that's why I call it dynamic system. Because you have dynamic system, your output and input is always kind of have certain kind of delay. It takes time to respond. So this is a typical curve for kind of a system response. And this is actually how we identify a system. We want to see how a system performs. If you have, say, a supporting structure, we want to know what is the response of this structure, or what's the dynamics of this structure. You can use a hammer, just hit the structure with impact, or you can shake the structure, then you have an accelerometer to measure the signal. It will be something like that, okay? Or it will be like that. But that's not a step response, that's an impulse response. If you give say a motor, you just give it a constant signal and see how the input kind of change. So this is a feature of the system. Without control, it will be a different response. With control, it will be a type of the response we want. So in the previous fuel cell, I say the classic, modern control theory, we can get a perfect controller. When I say perfect, it doesn't mean you can do whatever you want with the system. You can get whatever the best performance you want. Perfect means you can get the best trade-off for a control system. So control system is always about trade-off. You don't get best of everything. So let's see what we want to achieve. So firstly, for a control system, we want to achieve is the arrow. The final arrow of the input and output needs to be very small, ideally 0. So that's one thing. The arrow needs to be small. Secondly is we don't want the signal, the output signal, to go too much. That's overshoot. If we set it as 1, we don't want to go to like 100 and then come back. Okay, we want to go a little bit over. That's overshoot. And the third thing we want to do is the rise time. So we want a system follow the input quickly. We don't want to take ages before the system output follow the input. And there's a setting time. So this is how long the system actually, the output gets to a small range of arrow with the input. Then after that time, it will within that band. The output will be within that blue band. So if you look at these things, particularly you look at this overshoot and rise time. You cannot push your rise time as short as enough without sacrificing your overshoot. So that means if you try to rise up quicker, if you're trying to do this, then you must have a bigger overshoot. Okay? If you want to have smaller overshoot, you must have a longer rising time. This is a feature of a dynamic system. So when you do control, what you do is you change the feature of this dynamic system. You're putting more poles and zeros to the system so you'll be able to get better. But you can't really ignore the physics here. You won't get a perfect system, just go straight and go right, perfectly input equal to output. Okay, so you have to get a trade-off in your situation. Is the response time more important than the overshoot, or the other way around? So you choose the kind of the best trade-off. So just that's also an important concept. Even you don't know how to design system, those are the ideas should be in your mind. You shouldn't think about, I'm going to get a perfect outcome. You can't. Nobody can. So example of control system. For example, you're going to drive your vehicle, follow the road. So this is kind of self-driving cars. It become kind of more of a popular thing. Maybe in the next 10 years, we'll have a self-driving car on the road. So the point is trying to have the car follow the trajectory of the road. Okay? So this is not a hard question. The hard question is because of the disturbance or the noise of it. If somebody standing there, what do you do? There's people standing right in front of you. What do you do? Or if there's a rock right in front of you, what do you do? It's all about controlling, avoiding those noise, disturbance, and unpredicted situation. Right? Another example is a robot control. So this is a kind of most popular robot, Puma 560, normally used in laboratory environment. What we want a robot to do normally is the TCP, the end of the robot, to go follow certain trajectory. And the robot is made of, it's very hard to do this, with all the motors, with the rotational movement around the motor. So this robot has 6 motor. This robot has 6 joint, we call it 6 joint. We have microcontroller controlling each joint, go to certain angles, and the combined effect for that is this robot is going to follow the trajectory. Each one of these computer will get the motor output as a feedback. So at each joint, you have some encoder to measure the actual motor position and send that information to the microcontroller. The microcontroller do some calculation based on the main computer will tell each microcontroller where this joint should go. And based on the difference, it will keep going and until it reaches the desired position. So in this case, we have like 6 controllers control each one of the joints and trying to synchronize the movement to achieve a certain robot position. Controller design, it's like your mechanical design. I think most of you guys did the 215, 311. It's the same process. You have to go through try and error. You kind of, it's not a linear process. You're always getting to some problems in the end. If you can't really address the problem with your current design, you basically have to override and come to a complete new design. So the design processes, you have to always be kind of consider it's a nonlinear process, and if it doesn't work out in one way, you have to restart and do the design using other methods. So for example, if you're going to do the lab, you would design certain kind of algorithm to control the temperature of a water tank. If your initial idea doesn't work out, you might consider, I might need an extra heater to heat the tank. I might need an extra pump to get extra water to the water tank to get the job done. So there's a lot of freedom in the design task, but also that means you might get to the wrong track. All right, so just a summary, the dynamics of system is important. You have to know kind of roughly how the system responds to the environment. So you can do some mechanical or electrical kind of testing to measure the dynamics of system. Like I said, if it's a mechanical system, you can use a hammer to hit the structure and measure its oscillation. If it's an electric system, you can give it a certain voltage, a certain waveform that measures the output to kind of identify the mathematical model of a system. So if that can be done easily, it will help you a lot because you know how the system performs to start with. Then you can design a system with kind of more guidance from mathematics. And if that's not the case, if your system is just too complicated and you don't have any idea what the parameter the system is, then you start from blind. It's more likely you kind of, the first trial of your controller is going to be horrible performance. You don't get what you want to system to perform. But even that's the case, you can go towards a simpler controller like PID controller or switching controller to get certain kind of performance you want. Then that becomes a try and error kind of method. We almost never going to do analog electronics. So that's the history. And now it's more of a computer or microcontroller. If you learn from SECTI, you probably know those microcontroller. And this subject we're going to learn some PLC, interface and control. So you will, after this subject, you will have some kind of methods for you to actually implement a controller for your particular task. So let's keep reviewing this. The performance of so this is about the modern control theory. You can see there's a lot of crazy things here. A is the matrix. A is the matrix. This is the model of system. So A is the matrix, and B is the input relationship, and C is the output relationship. So basically, most critical is the A that represent the model of your system. And the performance of the system is completely dominated by the eigenvalues of A, or this is the same thing as the pose of your transfer function. These are the same thing, exactly the same thing if you mathematically derive them. So the open loop performance is by that. So that's without controller. Then if you have a controller, you can change its performance by changing this K. That's your controller. To make the system perform what you like by moving the pose to a new location. So that's about the modern control theory. But it's hard. Like I said, it's if you don't know the theory, this is not a feasible way to go ahead. And it requires A, which is the system dynamics, the model of system. In most situations, you don't know. You don't know what A is. So you just go straight to PID, which is doesn't require the model. We just try and error, get it working roughly. It's low cost, easy to implement, and get mostly the job done. It's not perfect. You don't get best performance, but it's good enough for most situations. So let's look at PID. We watch the video. Basically, it's three terms add together. Proportional. So the input to the PID controller is the arrow signal. So that's the difference between the reference and the output. So the arrow message is your input. And for the controller, it has three gains. First gain is KP. This is the proportional gain. You can see it multiply with the arrow signal. So this is ET. So we call it proportional. It's the proportional to the arrow signal. The second term is KI. This is the integral signal. So it's adding all the historic arrows together. Then this gain applies to that total arrows. The third term is KD. This is checking the change of the arrow. It's multiplied with the difference of the current arrow and the previous arrow. So just to see if the arrow is kind of approaching to zero or if the arrow is getting bigger and bigger. And these three things, one is consider what happened now. Because arrow is the current arrow. So KP function as what's going on at the moment. If the arrow is big, there's a big difference, I wanted to control it. So getting a KP and use that to drive the system. KI is like holding a garage. I remember we have big arrow historically in the past. Even currently you have your arrow is zero, doesn't matter because you used to have some arrows. I'm going to punish that error. I'm going to adjust your system based on that. This is the KI is the way to get rid of the steady state error. Okay? If you imagine we don't have KI and KD, only have KP. What's going to happen is if there's no error, the controller is not going to work, then the process is not under control. The process can't go anywhere, right? So the only way for the system to be closed and perform in a steady state is when there's a small error presented, and your KP is based on that small error. So that's called a steady state error. If you only have KP, your output is never going to be the same as your input because you rely on that small error to control your output, or control your system. So you're always going to have steady state error. However, if we have the history there, because history tells me there's some error there, this is going to punish that steady state, and eventually you have no error. The steady state will become 0 because if there's some steady state, this thing is, remember that, is going to continuously punish it until it goes away. Okay, so that's very important to kind of, based on the historic difference, we're going to do some something. KD is what we call the differential term, or we can call it a predict term. So this is about how fast the error is changing. You might say, oh, the system doesn't have much error now, but you can see, what happened is last step, the error is super big. Then this step is only no error. Okay? But the controller still want to punish it because it can predict the future, because the future is going to go this if things are going kind of linearly. Even at the moment, there's no error because the trend of the changing is too much. I can predict in the future is going to go negative. So for that reason, I'm going to punish the system now to avoid it's going too much kind of compensated from the P and I. So KD is kind of having magic to predict what's going to happen in the future. But in most, or in many cases, KP and KI is enough. You don't need a KD. But in some situations, you put a KD and make things worse. Depends on the ratio of this KI, KP, KD. If you just Google the PID control from internet, there's a Wikipedia link here. You can know a little bit more details about that. But like intuitively, that's like KP is doing control based on the current situation. KI is doing based on the history. So KI holding a grudge for a very, very long time or forever. And KD is trying to predict the future. So with all these three, you have kind of very strong team working together to provide a very good control output. In reality, we don't want to go that far. So let's see an example. Say if you're taking a shower, the temperature is not ideal because we all have experience, right? Particularly now is in the winter. When we turn on the shower, it's very cold at the beginning. It will be cold for like 5 seconds, 10 seconds, depends on what kind of heater you're having. Then it goes to probably too hot because normally you tap on to the maximum hot water, but it become too hot. Then you have to tap down a little bit. Well, then it might become too cold again. So it might have something like that. And normally what we do, we manually is kind of, we know the experience. Like historically, the tap needs to be in that position. So remember, okay, that's the position where I get perfect water. So at the beginning, you turn the tap full on, hot water. Then after like 5 seconds, you tap to, that position is normally I got good temperature. You just keep there. So that's based on your understanding of the model. You do that. If you have a controller to control this temperature, we want a controller to be very simple. The easiest way to do that is we have a on-off control. So one situation for that is you normally don't try to turn your heater up and down. What you do is I either turn the heater on or I turn it off. Okay, so normally I will just heat off if it's heat off if its temperature is too high, then heat on if the temperature is too low. But we create a kind of threshold. Say if this is 40 degrees and up and down a few degrees, that's a comfortable zone for me. Then you just have a kind of switch, electrical switch over there, control temperature by turning it on and off. This is called a band control. I'm going to mention that in the next few slides. So most common situation in industry is you don't have a continuous control of your actuator. Okay? In many situations, you don't have continuous control. What you have is I can turn this on, I can switch that off. You have those kind of on-off situation. In that situation, PID control will become quite harder to do because you can't really tune up and down your control signal. Your control signal only have like on-off stage. If you do PID control, you might end up to you switch that thing on-off very frequently and damage it. So in that case, we just do this on-off control and switch control. So let's look at that situation. So overall, this group of controller is called intermittent control. In comparison with what we learned, continuous control. So this continuous is not meaning the digital and the continuous control. It's a different term. This continuous control means our control signal can change in kind of continuous magnitudes. Okay? We have a continuous adjustment for our control or input signal. Intermittent control means you don't have continuous kind of adjustment for your inputs. The input is either just on off. So this two is you only have your input as on or off. Say you have a heater. So this example is your fridge, your aircon. Mostly is working in this condition. You don't like fridge don't work at like half load or full load. What the fridge do is I'm going to be on for a certain time, then off for a certain time, then on for a certain time. You're doing like that. Okay? So this is a turning on, turning off. If you adjust the temperature of your fridge to be higher or lower, the controller did is I switch between this time, T on and T off. I make this time ratio slightly different. Instead of trying to make the compressor work in different mode, because that's just easier to do. For your air conditioning, that's the same thing. If you tune the temperature, it just means your AC is working longer or shorter instead of you actually AC is going to output different values. Okay? So in this situation, we use intermittent control. So on-off, two position, or floating control. And when we do our PLC, in the actual lab, we are actually doing this kind of control. It's more about the logic between input and output rather than dynamic kind of control system. So first, intermittent control is on-off control. So this is just an idea. Actually, this is not a kind of actual usable strategy, but it's idea, and then it brings to the second one. This is actually what we use. Okay, this is actually what we use. The first one, second one, first one brings the idea. So the idea of on-off control is if we have our input is kind of less than the setting value. So this is our setting value. If the output is less than that, we switch our controller to a stage, either off or on. If the measurement is larger than that, we switch to a different situation. So basically, we have a reference. For example, if we have air conditioning, we set the temperature to be 30 degrees. Then if it's less than 30 degrees, we turn on the air conditioning. Less than 30 degrees, we turn off the air conditioning. If it's more than 30 degrees, we turn on the air conditioning. So we want to say, make sure the temperature, this is 30 degrees all the time. But you can obviously see the problem here, right? What happens, the temperature is fluctuating between 29.9 and 30.1. So what happens, you switch on your aircon, it drops to 29.9, then you have to switch off, then it goes back to 30.1, then switch on, then you become like oscillate between this on and off. So the fix for that is we actually create a data band. We create a data band. So this is our set point. Say this is 30 degrees. And our AC don't take action with that. And we have another value we call this is PV, is the process variable. Oh, sorry, no. We have forget what we call it for this is arrow band. Sorry, this is called arrow band. So this is how big the arrow band. Let's say the arrow band is 5 degrees. Then this is 25 degrees. That's 35 degrees. It's a little bit too much, I think, in this case. So what happened to this air conditioning is instead of we trigger the action at 30 degrees, it doesn't do anything until it's 35. So once the temperature goes to 35, it will turn on the air conditioning, so your temperature goes down. Let me change on a different color. So your temperature goes down because you turn on air conditioning. Going down, going down, going down. Go to 30, we don't do anything because that's only the reference. And until 25, this is our lower limit. Then we turn off the air conditioning. So stay there. Then what happens, the temperature is gonna, you switch off. So this is off. You switch it off. But what happens, temperature is gonna go up. So this part is not under your control, it just goes up. Until 30 degrees, you still don't do anything. And when it goes to the 35, you switch your aircon on. So you create this data band. When your signal is within this data band, you don't take any action. When your signal is lower than your lower band, you do something. And then when the signal is higher than the upper band, you do something else. You switch on or off. So either this side be off, this side be on. Right? In between is no action. So this is called a two-position control or on-off control or band control. There's a few different names for this kind of control system, but this is kind of the simplest control we can have. Like if you have a heater, or you have some machines will have a pump. You pump the water to a tank. So you can easily just turn it on for a certain time. Once the water is enough, then you stop. Then once the water goes too low, you turn it on again. So it's very easy to do. And implementation is quite easy. You can see the logic here is you need to do two things, right? You have to compare the temperature. So system temperature, your measured, and your set point. Okay, so normally this needs to be, sorry, I think it's the next slide. No, I don't have a next slide for that. So this is in the set point plus or minus the bandwidth. Okay, so when your temperature is less than that, you take action. Then when your temperature is more than that, you take another action. So maybe that will be heater off. There's another block doing the same thing. So one is plus, one is minus. Right? So that's kind of very simple controller. And this is basically just compare two values. This block is actually a PLC kind of ladder logic module. This is comparing two values. and this is your action. So this is you connect to the output. Then normally that connect to a relay to switch something on or off. Okay, so this is the explanation of that block. So basically you have two inputs. One connect to your setting value. The other one connect to the temperature measurement. So this all goes as the input to the PLC. This is normally just a value inside your PLC. This goes to the output of the PLC to control the relay. So very easy to implement compared to, like, say, PLC or even other crazy controllers. If that's not enough, but we don't want to go to a full kind of continuous controller, so some of the machine you can say set up into a few stages. You can say the heater is completely off, and the heater is half on, then the heater is 100% on. You can set up into different stages, but you can see if we have a lot more stages. You have, like, say 100 stages here. Basically, it's a continuous control system. Right? So sometimes you call this floating control. It's just have a few middle stages you allow to not just on off. You can turn the system into a certain percentage on. All right, so we've done all those control-related reviews and introduced this simple new kind of control idea or on-off control idea. Now let's go start talking about the PLC. PLC pretty much is just a computer. It's kind of a specialized computer for industrial applications, and it's coming from relay logic. Anybody knows what relay logic is? Anybody has, or if you are kind of cadet in BlueScope, or if you work in the factory, you probably do, but I think anybody actually has experience with the relays logic stuff? No? Well, this is a very popular with those logic control in industry before the PLC. The PLC is kind of starting from 1970s, so similar time with computer. So at the beginning, it's called a PC, programmable controller, for a few years. Then people realized PC is short for personal computer. It's very confusing, but personal computer is a way more popular name. So they changed the PC to PLC, becomes a programmable logic controller, because that, like, what the PLC trying to do is control the logic, the complicated logic to switch things on and off. That's what PLC is good at. And before the PLC, it's all this relay logic with a lot of switches, and it's a physical switch and capacitor, resistor, inductors. It's like analog kind of circuits, but this is kind of control logic circuit. And PLC is used to mainly replace those, make all those logic implement not by physical relays and switches and components, rather to implement those logic inside software. So let's watch another video.
Quick! A programmable logic controller, or PLC, is simply a special computer that is programmed to control certain processes in industries like petroleum, steel, or automotive. Every PLC is composed of three main parts: input, CPU, and output. Suppose that we have an electrical motor and a push button. We want the motor to turn on when the button is pressed. When the button is pressed again, we want the motor to turn off. This function is similar to the function of the power button on your TV remote. To do this, we must first write a program for this operation on a computer and then download it to the CPU. Then, we connect the switch to the input and the motor to the output. Now, if we press the button, an electrical signal will be sent to the PLC. The PLC input will deliver this signal to the CPU, but first must present it in a format that the CPU can process. Why? Because the CPU is a computer system and cannot process the raw electrical signal. The CPU will process the data received and send the result to the output. The output turns the data to a raw electrical signal again and applies that to the motor and turns it on. Now, if we press the button again, the process repeats and the motor will turn off. Okay, if you like this video, subscribe to stay updated with our new videos.
There's many good YouTube videos in PLC related areas. Particularly for this week and next week, we're doing kind of more general introduction. So some of the concepts, probably the video provide a better explanation than I can do because they have very good animations and explanations. So I will encourage you to search for those terminology if you don't fully understand or if you wanted to know more. Just go Google. There's a couple of very good YouTube channels I'll probably recommend next week. There's quite a few very good ones explain the things very, very clear. So PLC basically is a computer, but it's special by the strong input and output capacity. These are different kind of settings. Why we need so many settings? Because for different application, the number of kind of connections change dramatically. You might have only a few simple stuff to control. For another situation, you might have hundreds or even thousands of different input-output in the process. So particularly for PLC is expandable, something like this. Is an expandable module. You have your main computer, you have your communication card, and all this is kind of input-output terminals. You can connect to many different input and output, and it's expandable. You can have more modules next to it if you need to expand. So it's like a computer, but its strength is only input and output control. This figure gives you a few examples of Allen Bradley PLC. If you look at the structure, architecture of the PLC, it's a microprocessor or CPU. Then you have a memory, which is your program. Then you have input output. And this is the most strong part of the PLC. Handle way more different voltage, current levels compared to PC. So your PC input output normally is like 5 volt, 10 milliamps, but PLC needs to deal with a lot of industrialized kind of equipment, which runs in many different voltage, current, sometimes it's AC voltage, some DC, like so many different ways of signals. So that's extremely important for a PLC, and that's the main difference. But in the end, it's just a computer. So I think in 2007, or before the global financial crisis, the market of PLC goes like 20% every year for a few years. And after that, it slowed down a little bit, maybe goes 2 or 3% every year. In 2017, this is an $8 billion market. So you can imagine there's a lot of companies in PLC. And the most common ones, I would say, is Allen Bradley. And this is the one we're going to kind of study in the subject, the week 1 to week 5. All the kind of problems are based on Allen Bradley. So all these PLC, they use a very similar way of programming, and many of the grammar are the same. However, they all have slightly different ways of doing their things. So for that reason, for the labs, we're using Siemens PLC. This Allen Bradley is mainly in US, and Siemens is mainly in Europe and the rest of the world. I guess US is always different from the rest of the world. So these two are the kind of major two types. There will be Rockwell, Snyder, Omron. So these five is probably the biggest five. But from the major category, like from the US type is Allen Bradley. From the Europe type will be Siemens. If you know these two, then the rest of them will be very similar to one of these. So their idea will be slightly different, but the majority of the things we're going to go learning through Allen Bradley. I put the manual for Allen Bradley and Siemens PLC on the Moodle website already, so you can go have a look. And if you have particular question about part, you can just Google and find more information. Like I mentioned, so the PLC is trying to replace the relay logic. That's where why the PLC is invented and what's PLC trying to do. It's like the digital circuit replaced analog circuits. So before the 1970s, everything is implementing this relay logic to achieve those industry control. And now it's kind of more and more replaced by PLC with the cost of the PLC getting lower and lower. But you still can see some of the relay logic, and relay is still there. You don't completely get rid of the relay, but a lot of kind of logic stuff is not achieved through this relay. Instead, it's achieved inside the PLC. So this is figures of a relay. There's many different kind of looking of the relay, and it's a single pole, single throw. Single pole, single throw relay. So what's the pole? Pole is also called this armature. It's the movement of the movement part of the relay. So how the relay works is that you have a coil. This is going through some electric. You have electrical signal go through and connect to some. This will be a control circuit. That's your control terminal. If you put current through this coil, you generate magnetic force, and this armature normally is made of steel. Will be having the force pull to connect with the coil. Okay. So in this setup on the left side, you will see if the coil is kind of have the signal going through, what happens, this armature will move to the left, and this switch will be moving to the right, then it will make the switch become open. On this case, if the coil have current go through, what happens is that this armature, this metal will be pulled up by the magnetic force, and this switch will be go there and close it. So basically this shows two different type of the relay. The first one is normally it's closed, and when you power it on, it will be open. The right hand is normally it's an open switch. So we're looking at this circuit. Open or close, we'll look at this circuit. This is our circuit. So the switch normally is open, means the circuit is open. You don't have current going through the circuit. But once your control side turn on, then this switch is going to be closed because this two contactor is going to move up and close it. Then your circuit has current go through. So this is a very simple kind of using in the coil. This is a low current, low voltage, and in here will be our working part will be high current, high voltage. Okay, that's a typical industrial setup. The low current, low voltage stuff is controlled by your other circuits or your computer, and the high current part is your motor, your machines, and other things, which draws a lot of current. So there's an insulation in between. This black matter is an insulated matter, so separate the electrical signal between the low current part and high current part. If you have a lot of this kind of equipment in there, you can build up a very complicated logic to achieve certain control tasks. I have to take another break. Let's say